Okay. So a slope field. What is a slope field? Do not tell me a field of slopes.
Don't you love running outside?
Draw the lines based on what the coordinates are.
Okay. So it's a graph. I'm going to call it a graphical representation of solutions to what?
Differential equation.
Differential equation. Okay. Now, lucky for you, since you've been through AB, you know what I'm talking about with the differential equation, and you've solved them before. And even when we talked about slope fields in AB, you had seen them a little bit, just not like the separable ones. So a differential equation looks like this: dy dx equals blah, 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 blah. Okay? Now, this is one that we can solve. We know that y equals 1/3 x cubed plus c. We know that, okay? But there are going to be some that we cannot solve with the tools that we have currently. And so a slope field is a representation to where we can get an idea of what's happening without actually having to do the calculus part of it, okay? So a slope field is, you know, what it sounds like, a field of slopes, right? That's representing these solutions. So when I ask you for a slope field, you are literally drawing me itty bitty tangent lines. Okay? So dy dx equals x squared. At the coordinate 0, 0, dy dx equals, so we draw an itty bitty tangent line with slope 0. At the coordinate 1, 1, our dy dx equals 1. So we draw an itty bitty tangent line with slope 1. Okay? Can I trust you to draw these slopes on your paper as I draw them on my paper and we think independently of each other?
Yes.
Okay. Does your slope field look like my slope field? Okay, so this is a graphical representation. Remember, we have an infinite number of solutions that could be a solution to our differential equation, okay, because of that plus c. Now, if, like, I kind of think this looks like a wind map, right? Like the little lines, the wind direction, okay? If we were to follow where the wind blew, what do these look like?
Cubic function.
These look like cubic functions. Strange, because we have dy dx equals x squared. Well, if we take the antiderivative, because we know how to solve this differential equation, we know that our solution is 1/3 x cubed plus c. Here we have a bunch of 1/3 x cubed plus c's, okay? And so whatever your differential equation is, this slope field represents those solutions. So y equals, or whatever equation would we be able to get out of it, okay? Now that one was kind of boring, but you know, we gotta start somewhere. Let's go ahead and go to the next page. And let's go ahead and look at this one. okay? dy dx equals x plus y. That is not a differential equation. We could separate and do separation of variables. You know what that is, so I can talk about it. But we cannot solve that with the tools that we have. The only way for us to really understand what's happening in our equation is to look at the slope field. Okay? So let's take some time and let's make these slopes. So x plus y is our differential equation. So at 0, 0, we have a slope of 0. But at 1, 0, we have a slope of 1. And at 2, 0, we have a slope of 2, etc. Okay? So let's take some time and fill in all of these slopes to the best of our ability. Okay, does your slope field, is it starting to look like mine? Are you seeing a pattern here? We kind of have some diagonal patterns happening, right? Since our differential equation is x plus y, we have along the diagonals the same slopes. Now, do you see a place where all of the slopes are -1? Okay, this right here. Okay, what's happening there? We have an asymptote. Okay. So when I ask you for the solution at 0, 1, this coordinate right here, we have to take into account that at this line right here, there is a slant asymptote. Okay? When I ask you to draw in the solution to a curve, you need to follow the slope of the slope field. So I can see as we move this way, our slopes get steeper. And as I move this way, I'm going to have to level out to a slope of 0 before I turn and hit that slant asymptote. Okay, so I know that I'm going to have to hit a slope of 0 and then approach this asymptote. And then as I go this way, my slopes get steeper and steeper and steeper. Okay, there would be the solution to our curve. Somebody's very excited next to me. Okay, now there are two different matching pieces on this piece of paper. Okay, here I'm matching potential solutions. Here I'm matching their differential equations. So remind me, what do, oh man, I forgot I have to erase everything. What did our slope field represent?
Is it graphical representation of solutions to a differential equation?
Solutions. The solutions, right? Okay, so when I'm asking you to match these, what do we have to do?
We need to find the problem.
Okay, so what does this look like? What kind of curve?
Sine.
A sine curve. Yeah,
Almost said squiggly line.
those are sine curves. Our solution is y equals sine of x. Okay, these are the solutions. What does this look like? It looks like a cubic function, doesn't it?
Yep.
Okay, that's our solution. It looks like the solution. Okay, now, that's nice. But these are the differential equations. So we have to think about how these affect our slopes. So I'm going to give you 2 minutes at your pods to determine what matches where.
This one's will be 6. We can just get rid of that one.
How do you know that?
Well, because the derivative of the sine is a cosine, so it's always going to be a squiggly line. Sine cosine.
Squiggly lines. Lines are not squiggly.
They are.
Lines are six.
Yeah.
It's going to be, yeah, unless they're
The
squiggly.
oscillation line 6 is going to be double.
This is squiggly drawing.
How do you know that was a
Because when you plug in y, it's always going to equal
Where
0.
it equals 0.
So when you plug in 2 here, it's always going to equal 0. So add 0 here. I mean add 2 here, so it's always 0.
I think 4 has to be.
So really what you do is you just plug in the answers.
Okay, I'm guessing F.
Yeah, because so this one looks
Yes.
is this
E to the x
It
is
also
just
tells me I
going
will.
It looks like e to the x, okay?
Unless the derivative of e to the x. Unless the antiderivative of e to the x.
Alright, x over y. That's like the
Okay, then the x one is just
so that leaves us with 3 that don't have answers yet.
Well, don't look over.
See,
then how is that? What?
Are we not until
2,
30?
2.
Okay.
yeah,
Zero here.
Benjamin,
What?
what is A?
A is most certainly one of them. I haven't figured it out yet.
Okay. How about B?
B I think is 4.
And why do you think it's 4?
Because the antiderivative of x is something x squared. So that looks like an x squared, right?
That's a good rationale. Okay. Zane, what's A?
A is number 3.
And what stuck out to you about A that you paired it with number 3?
I said that there's like at 2 there's some sort of straight.
Okay, so at y equals 2, all the slopes are zeros. Okay. Where did it go? 2 minus y. So 2 minus 2, 2 minus 2, 2 minus 2, all of those are going to be zeros. That's good. Okay. C, Richard.
So 2.
Okay. Anything stick out to you in particular about that?
When they're the big ol' x.
Okay. So like when we have either opposites or the same for x and y, we're getting slopes of 1 or negative 1.
Yeah.
Okay. Good. Isabel. D.
6.
And what stuck out to you there?
And squiggles.
Yeah.
Okay, we have that oscillating behavior. Okay. Let's see. E. Marina.
Because when
Well, tell me the answer first.
I would be
Oh, okay.
at 0, 0, they have the horizontal, and then it continues on like that.
Okay, so anytime x and y are opposite, we have that zero slope. Okay. Haley, we only have one left, but what's the answer?
Number 1.
Okay, and what stuck out to you about that?
I'm not really sure.
Okay, let me ask you this. What's the antiderivative of e to the x?
E to the x.
E to the x. What does this graph look like?
E to the x.
It looks like e to the x, right? Okay, so that's a nice one to pair up. Okay? All right. Very good. Okay, I think we Okay. AP problem. Woohoo! Okay, let's go ahead and let's work on this together. Anytime x and or y are 0, what's the slope going to be?
Flat.
Undefined.
How about 0?
Oh, never mind. Just kidding.
They're in the numerator, right?
Just
So along the x and the y axis, you have slopes of 0. Okay. Okay, at 1, 1, we would have a slope of 1/2. At 1, 2, we would have a slope of 1. I'm going to go ahead and reflect that with our negative. So, negative 1/2, negative 1.
2, 2, we have a slope of 2.
2, 2 would have a slope of 2.
Yeah.
And what about 2, 1?
That would have a slope of 1.
Okay, so I'm going to go ahead and reflect those over here. Let's see. 3, 1 has a slope of like 3/2. And wait. 3, 1. Yeah. 3, 2 would have a slope of
3.
And then down here we have positive 1/2 and positive 1. Negative 1/2, negative 1, and negative 3/2. Okay, I know that was kind of quick, but let's get to the good stuff. Okay. All right. Let f be the function that satisfies the differential equation. Write an equation for the tangent line to the curve through 1, 1. Okay. Zane, what's our slope at 1, 1?
1/2.
Okay, so we have y minus 1 equals 1/2 times x minus 1. Okay, we are going to use this tangent line to approximate 1.1. The y value for x is 1.1.
1.2.
You already did it. I said it wrong. I'm saying the answer instead of the problem. 1.2. Okay. 1.2 minus 1
0.2.
divided by 2
0.1.
plus 1.
1.1.
Thanks, Richard. Now, turn to your neighbor and tell them, is this an over or under approximation? How do you know?
Oh. Ooh. For 1, 1. Oh, that's easy. It's an underestimate. It's under.
How do you know?
Because it's concave. So it's concave.
Yeah,
But that's the but that's the derivative.
Yeah.
So then we need to
slope.
think of the.
Well, no, this is okay. Think of it like this. This is the slope, right?
Well,
You
it's
can
a
you
box.
know what the graph looks like just by looking at this. You can see it goes like that.
Okay,
Concave up at 1, 1.
Chris,
Present
under or over?
under.
Under approximation. Matt, why?
Okay, so we know, he already said it's concave up, right?
Nope.
No, okay,
All
so,
he said was under.
I said, okay, so it's under because it's concave up because the slopes are increasing and that's the definition of concavity.
Okay, we can look at our slope field and tell that we are going to be concave up, right?
Yeah.
So since we are concave up, we have an under approximation for our tangent line because it sits below. Okay. What's nice is since we have a slope field, you don't have to calculate the second derivative. You can look at the graph and know. Okay. All right. On to the new Euler's method. Okay, now let's talk about this. we had a tangent line. And the further we walk out on the tangent line, the
Farther away you are.
The
from
farther you are away from the truth. Okay? Or really just the real Y value.
the truth.
Right?
Okay.
Okay? If we have a tangent line, the further we get away from that point, the less accurate we are for the Y value of the true curve. Okay? So, Euler came up with a method for us where instead of walking out on a tangent line, we walk out on a tangent line and then we reassess our slope. And then we walk out on that tangent line and then we reassess our slope. And then we walk out on that tangent line and however many times we need to do it. Okay? But instead of one tangent line, we take a tangent line and then we take a new one and then it kind of just, it's going to fit a little bit closer to our curve as opposed to just one big tangent line. Okay? Let me zoom in on that. That wasn't a good picture. Okay? So here's like, we're like super zoomed in. So I move along this tangent line and then at this point I make a new tangent line. And then at this point I make a new tangent line. And it might not be tangent to the curve, but it's using the slope from where we are. Okay? So, in order to do that, we're going to start out with a coordinate, and we're going to figure out what its slope is. Derivative, right? And we're going to use that, okay? Let's take a timeout right here. Slope is change in y over change in x. Do you agree? Okay. So, if I rearrange this, our change in y is the same as slope times change in x. Are we okay with that? So what we're doing, we're taking our point, we're figuring out our slope, and then we're moving along just a little bit. Okay? By figuring out what our change in y is. Okay? So if we're moving along, if we start at like 1 and our change in x is 0.5, then at 1.5, what is my y value on that tangent line? And that's what we're figuring out right here. Okay? Then, starting there, we're going to do it again. Okay, now I have a new xy coordinate. Let's take this and make a new tangent line. Okay, so we figure out the slope, we figure out the change in y, and we have a new coordinate. Okay, and we do this as many times as we need to. Okay, the change in x will be determined by how many steps you need to take and how far you need to get. What's going to help us be more accurate to the true curve? Okay, more steps that are smaller. The more steps we take, the closer to the curve we're going to be. Okay? Is everyone understanding like the analogy of what's happening?
Yeah.
Okay, instead of like one tangent line, we're just kind of like breaking it into little pieces and making new ones.
What's different from this to a slope field?
So, we're basically taking, so in a slope field, you don't see all of the slopes, do you? No. So we're strategically taking the certain pieces of the slope that like fit along our line. But in a slope field, we just have kind of random lines drawn. Here, we're actually calculating which slopes we need to use. Does that answer your question?
Yeah.
Okay. So, back page, example. Here's our differential equation. Yes, I know we could solve this. However, there's going to be some we can't solve, like the second example on that page. Okay, you've turned the page. Okay. The second example on that page we couldn't solve, but I want to do one that we can solve just so we can kind of compare. Okay? So this is our differential equation. Here's where we begin. We are approximating y of 0.8 with 2 equal steps. Okay, so our steps, we have 2 steps, which means our change in x is going to be what? How did you get that, Richard?
0.8 divided by 2.
Okay, we are ending at 0.8. We are beginning at 0, and we want 2 steps. So delta x is 0.4. Feels very similar to something that we've done in the past. Okay, so let's make our chart. Okay, your book's not going to have this chart. The math that they do is the same. I just think that this keeps it a little bit more organized, especially if we have multiple steps that we have to take. Okay, so we start out at the coordinate 0, 5. If we plug that coordinate into dy dx, what's our slope? Thank you. We want to plug x in to x and y and for y. Okay, so now our change in y, remember this is slope times change in x. We got to walk along our tangent line. Okay, so we take negative 2 times delta x to get okay. So I started at a y value of 5. Our change in y is negative 0.8. So our new y is 4.2. Now we are at the coordinate 0.4, 4.2. Okay, there was 1 step. Okay, this is just our change in x right here. Okay. If we do change in x again, we're going to get to 0.8. That's where we need to stop. Okay. So 0.4 comma 4.2, if we plug that into dy dx, what is our slope? Negative 1.6. And if we take our slope times delta x to get our change in y, we get negative
0.6.
Okay. Well, we started with a y value of 4.2. Our change in y is a negative 0.64, which lands us at
5.6.
So our new coordinate is 0.08, 3.56. Okay, now we're kind of running short on time. If we did the tangent line equation, we get 2.6. If we did the actual value, we get 3.72. So this is a lot closer. Okay. It's not like exact, and it's not going to be exact, but it's a heck of a lot closer than following the tangent line out. Same. Now, let's just talk through that second example before we pack up for the day. In our second example, we would have to use Euler's method because there would be no way right now that we have the tools to solve this differential equation. Okay? We need to take 5 steps to approximate 1.5, and we're starting at the coordinate 2, 3. What would our delta x be? Okay, we're ending at 1.5. We're starting at 2 with 5 steps. Okay, so that would be our delta x. And you would have to go through 5 times in order to get to our coordinate. Now, we are traveling a shorter distance with way more steps. So this example right here is going to get us a much more accurate answer than we did up in the first example, because we're taking more steps in a shorter amount of time. Okay. All right, let me get you your homework here.
I mean, you don't have to do that.
I really do.